Welcome back to a course on calculus RS integration. In this lecture, we are going to see a theorem based on the refinement of a partition. So, technically, this is the first theorem of this chapter. Given if P star is a refinement of the partition P, then we'll have to prove two things. That is, LPF alpha is smaller than or equals LP star F alpha and UP star F alpha is smaller than or equals UP F alpha. Okay, at the end of this theorem, let us do some interesting remark that helps in understanding the theory of RS integration. Okay, let us start the proof. Since P star is a refinement of what? Of the partition P, P star will contain at least one point more than P. So let us put them in this way. If P contains the points, that is x is equal to a is equal to x naught and what? X1, x2, xi minus 1, xi plus 1 and it goes till xn, which is b, with the condition that x naught less than or equals x1 less than or equals x2 till xn. So this has to be the condition. Okay, this has to be the condition over there, and p star is the collection of exactly the same but with extra one point, and that extra point, let us denote it as x star, and it proceeds this way. Okay, and this also satisfies the uh, conditions, the requirements. It has to satisfy the requirements. It has to come in a natural way, right? Now let me denote mi, big mi, to denote the supremum of f of x. If this is the case, xi, and small mi to denote the infimum of f of x for the same case. I think this is the convenient way of writing things. Okay, this and this are same, so it is now mi prime to denote the supremum of f of x in the interval x. Okay, in the interval x I minus 1 comma x star, and mi double prime to denote the supremum of f of x when x takes values in this interval. Okay, as we did for the supremum case, for the infimum case we will take a mi prime and mi double prime to denote the supremum of, sorry, infimum of f of x over the respective intervals, that is xi minus 1 comma x star and x star comma xi minus 1. Okay, now let us write down LPF alpha. So what is going to be LPF alpha? It is summation I runs from 1 to n small mi delta alpha I. So it is m1 times of what is alpha I? It is alpha of x1 minus alpha of x naught plus m2 times of alpha of x2 minus alpha of x1, and it goes till mi alpha of xi minus alpha of xi minus 1, and it goes till what? Mn alpha of xn minus alpha of xn minus 1. Let us mark this as equation 1. In a similar fashion, now we'll have to write L p star f alpha. Okay, it is going to be m1 times of alpha of x1 minus alpha of x0 plus m2 times of alpha of x2 minus alpha of x1, and it comes till what? Till m minus 1. It is well and good. Alpha times of xi minus 1 minus alpha times of xi minus 2 plus m I prime of alpha of x star minus alpha of xi plus mi double prime of alpha of xi plus 1 minus alpha of x star, and it proceeds with mi plus 1 alpha of x I plus 1 minus alpha of x, I suppose, right? So it has to be, what did I went wrong? No, yeah, that's it. So, wait, did I miss anything? This is, sorry, I x plus, right? So it is xi. Yeah, and it proceeds till mn times of alpha of xn minus alpha of xn minus 1. Let us mark this as equation 2. Now, using 1 and 2, we are going to do something. So, using 1 and 2, what I am going to do is that LP F alpha minus LP star F alpha. If you have a closer look at these things, the terms except these things, this quantity will remain, and in the previous thing, this quantity remains. All other things gets cancelled, right? So it is going to be simply what? Mi times of alpha of uh, xi minus alpha of xi minus 1. Here we'll have xi minus 1. This is where I went wrong. Sorry. So this quantity minus mi prime of alpha of x star minus alpha of xi minus 1 minus mi double prime of alpha of xi minus alpha of x star. So this is the terms we are left with. Now we'll have to check about these terms. What is it going to be? Now if you look at it in this diagrammatic way, you will have some better understanding. Actually these are still just integrable functions, but still let us try to visualize them as a Riemann integrable, and then the ideas can be extended to Stelzis. Or if you simply look at these things, your mi, okay, this is where your xi minus 1 and this is your xi, right? In this interval, your infimum value, the least possible value is mi. That is what we are saying. But in between we have introduced a point, and we split these things, and this is the minimum and this is some other minimum. Okay, the entire minimum will always be the smaller one. That is what we have used in this theorem, right? The entire minimum is the smallest one always. If you split things up in the smaller intervals, your minimum may be a bigger quantity than this. So using that idea, here we'll have to check few more things. This quantity, The terms inside this brackets, these quantities are positive quantities. Okay, and the ideology that I told is mi is always smaller than that of mi prime, and mi is smaller than that of mi double prime. Okay, and all these are positive quantities. Hence, what we may do is that we shall replace this with this. Okay, ultimately what we are going to get is that it is smaller than or equal 0. That is what I am trying to say. This is some positive quantity, this is some positive quantity, and this is some positive quantity. And here you may see that the okay, if you want, let me do things in a better way. Okay, let us have this quantity mi times of alpha xi minus alpha times of xi minus 1. Let me have this as it is. This mi is smaller than, so when I have to negate it, this from this, okay, let me do it in another color. This changes to what? Minus mi prime less than or equals mi. So this is what I need. And similarly minus mi double prime less than or equals mi. So when I replace that way, what I am going to get is that mi is taken as common, and I am going to have less than or equals. So minus alpha times of this quantity, minus times of minus becomes plus, and here minus alpha of xi, then minus minus becomes plus alpha of x star. If you see, these two gets cancelled and these two gets cancelled, and similarly these two gets cancelled. So your LP F alpha minus LP star F alpha is less than or equal 0, which gives you your LP F alpha smaller than or equals LP star F alpha. Let us mark this as equation 3. The similar arguments has to be done for UPF alpha. Let us do that too. Your UPF alpha is M1 M2 this quantity plus Mi delta alpha I, and it goes till Mn delta alpha n, and UP star F alpha is what? M1 delta alpha 1 plus M2 delta alpha 2, and it comes till Mi minus 1 delta alpha I minus 1 plus Mi prime of alpha of alpha of x star minus alpha of xi minus 1 plus mi double prime of alpha of xi minus alpha of x star, then mi plus 1 delta alpha I plus 1, and it comes till mn delta alpha I. Now your UPF alpha minus UP star F alpha, the things gets cancelled and we'll be left with what? Simply mi times of alpha of xi minus alpha of xi minus 1 minus mi prime of alpha of x star minus alpha of xi minus 1 minus mi double prime of alpha of xi minus alpha of x star, and the same arguments. This is the largest quantity, this is the smallest quantity, so we'll be left with mi times of alpha of xi minus alpha of xi minus 1 minus alpha of x star minus of minus plus alpha of xi minus 1 minus alpha of xi plus alpha of x star, and Just a minute. Here let us do the things. Mi is the biggest of these things. So we have minus. So minus mi prime bigger than or equals mi, and similarly minus mi double prime bigger than or equals mi. So we will have bigger than or equal sign here. So bigger than or equals 0, as this cancelled with this, and this cancelled with this, and this cancelled with this. So which implies UPF alpha is bigger than or equals UP star F alpha. Now for any partition lower is smaller than or equals upper. So in this result what we have proved is that this is smaller than or equals UPF alpha, and this is what we have proved. Actually here completes the proof. This is some remarks that I am marking. Okay, this is happening. So when you increase the number of terms in a partition, your sums gets finer. We are saying as we take the supremum and infimum of all possible partitions, the lower sum and the upper sum becomes equal when the function is Riemann integrable, right? So that will happen only when you increase the number of points in the partition, and this very well tells you that the integral value can be approached when you take more number of elements in the partition, and that is what we have done in this theorem. Thank you.